What's up, everybody? This is Matt Brown with another IoT hacking video. Today I have in my hands the Akita IoT Defender thing that will save you from all of the insecure IoT devices on your network. Well, that's what they claim, and their claims are many. We can look here on the box of this very professional device here. We can see that it tells us it will detect threats. You have no need to worry. It'll block hacks and malware. It's for every home. It's plug and play. It's just so easy to use. You're gonna plug this thing in to your network, and you're gonna be able to sleep at night knowing that your IoT devices are super safe because this extremely light and insignificant device is on your network. I don't know why, but some people thought that this was a good idea. About $1 million worth of Kickstarter funds or whatever, crowdsource funds went into producing this device. And we are going to go over to my workbench and we're going to take it apart. Like I said, sadly, this device is basically non-functional because the servers that it connects to are down. They've discontinued the project, but that will not stop us from digging into the firmware, and we're gonna poke around and have some fun, and then maybe in a future video we'll look at the mobile app that's supposed to pair up with this device and detect some threats on your network. I don't really understand how they were claiming it to work, but it's obviously a bunch of snake oil that we're going to figure out what kind of snake oil it is together. So we're gonna take it over to the workbench and get started. So here's the box that this came in. I definitely got this on eBay. I did not pay full price for this ridiculous piece of hardware. But inside the box, there's some pretty hilarious things here. So we get a couple of what look like, coasters. And so there you go. You too can join the guardians of high IoT, because that's what we do. We just we have our IoT devices secure, and then we put our drinks on our little coasters here. Here's their user manual, which is kind of hilarious because here you can clearly see that we're supposed to plug the LAN port into our router, and that's gonna tell us all of the bad traffic that is going from our router out to somewhere else on the internet, which is obviously not possible. So again, don't know how this is how they claimed that they were going to secure all your IoT devices that way, but we are going to open this device and find out, because that's what we like to do on this channel. If this is your first time on the channel, I like to dig apart into IoT devices, see how they work, find some security vulnerabilities maybe. So that's what we're gonna do to this. So let's just zoom in here. So I did crack the top open, and I've been poking around a little bit initially with this device, but actually before I do that, I want to show you kind of like the two paths I want to go down with this device. So obviously right here, we can see already populated. There's a number of pins here. There's 4 pins. And we have the male ends of the pins there. And then right next to it, we have a flash chip right there. And so those are gonna be kind of the 2 steps that we're gonna take in this video. We are going to connect to that UART interface, see what we can get out of it, and we are gonna dump the flash off of this device and see what we can do with the firmware image. And I think that's going to set us up in a future video for seeing how, like what the intention of that mobile app was. Like I said, this device does reach out to some cloud servers that are not functional anymore. But there you go. It's a big case, and it is basically completely empty, which is just hilarious. So what I'm going to do is I'm actually going to get this out of here. So that is going to be the first thing we're going to do. So looks like there's just a couple of screws. There we go. And there's something here that's kind of holding in the light So we're just going to have to pry this out somehow. All right. You know what? Ain't nobody got time for this. I don't need that LED to be illuminated. There we go. Oh, it slides out. Okay, well, could have told me that. All right, this is still like stuck to the bottom. It's making me think there's like a screw underneath here somewhere, which is hilarious. All right. Let me try to, oh, no. We got it. There we go. Okay, so there we have our device inside this, very, interestingly shaped object here. And so, but when we get inside, this is really all we got. This is all we got to work with. So we have power, we have two interfaces, but if you remember the instructions, it only tells us that we're really only going to be using one of those interfaces, the LAN interface, to connect up to the LAN interface here. And that actually matches some of my initial analysis, that's actually how it's going to work. And we got the power button right there. And like I said, here we have what is very obviously UART. They're not trying to hide it or anything. In fact, let's see if we can get any closer. Okay, let's go in with the microscope. And we will get that in focus. There we go. We can see that we have a very nicely labeled UART interface. So it's a little bit offset, but it's saying VCC, that's our voltage pin, ground, TX, RX. So now, actually, the only thing we really have left to do to connect up to this UART interface is just to confirm that the voltage is what we expect it to be, which is a 3.3 volt UART. To do that, I'm going to throw our multimeter overlay here, and I'm simply going to take my black probe on here. Oh, you actually have to plug the device in to take a voltage reading, as it turns out. So let's do that. So I'm just plugging this in here. We're going to depress our switch. Now we will actually have voltage. So there we go. And we have confirmed 3.3 volt is what this UART interface is using. So cool, that's done. I'm going to power the device off for now, and now we can scoot out of here back to the desk cam. All right. So we know we have VCC, ground. We don't need to connect up VCC because the device will be powered already through here. So we're going to connect up ground. We're going to connect our cable. This is our UART to USB cable. And so the pinout, you can easily Google the pinout of these cables. They're really common, but yellow on this cable is going to be RX of the cable. It's going to be the cable's RX, and then orange is going to be TX, and then black is obviously going to be ground. And so we are going to connect those up here. And the only thing that we have to be aware of, so on this little wire here, I have brown instead of black, but the brown's going to connect up to black. So the one thing we have to be aware of is that we need to swap TX and RX. So the cable's TX needs to go to the board's RX and vice versa, right? So, okay, this fell out. Let's put it back in. Here we go. All right, we got ground, TX, and RX. There we go. And then we're going to go plug into ground. Just confirm. Okay, so TX is going to go into RX, which is yellow. And the last one goes there. All right. So now we're all plugged in, And then the other end of that cord, I am simply going to put into my USB hub, which is hooked up to my computer over here. So let's pop over here. Don't need that overlay. And let's go ahead and let's run PicoCom. So PicoCom is just a terminal emulator that's going to allow us to interact with the device through that USB cable. We are going to guess what is the most common baud rate. That's the data rate. It's how many, you know, symbols per second are being sent over that wire. And then we need the device where that USB device is mapped into my Linux system, and that's going to be dev TTY USB 0. If there's more than one cable, it'll be USB 1, 2, so on. So we're just going to open that up. You can see now, like, we can't click anything because the device isn't powered on. So now we're going to simply power on this device. Oh, I unplugged. Here we go. Okay, now click, power on, and I'm going to hold down the Enter key because here we can see that it started to print out some information about U-boot. U-boot is a Linux, it's a bootloader that is commonly used with Linux-based embedded devices, right? It's an open source bootloader that are often used on these types of embedded systems. And so here we get some information about what version, the build and everything. It's a build from 2018, which is, you know, I mean, for some IoT devices, that's relatively recent. And then we get some pretty interesting things about the board, about the SoC and the CPU that are being used on this system, how much RAM, the flash chip we have. This is actually cool, so this is one way if maybe your flash chip, for whatever reason, was like, you couldn't read the serial number on it. Sometimes you can get that information from this UART interface. And so we have our device MAC address, some other information, but you can see that here it said hit any key to stop boot. So that's why when I powered the device on, I quickly came over here and I jumped on my Enter key, because that is commonly a way to interrupt the boot process of the device and pause inside of this bootloader. And we're actually dropped into a bootloader menu, which is kind of helpful. And so we can use this a lot of times to boot the device up in a way that helps us get root access or get administrative access on the device more easily than it would have been otherwise. So we can do things like, you know, print the environmental variables. And so if we wanted to mess with the boot of this system, we could, you know, modify this variable boot args. We could maybe set this init parameter to something else, right? But we're not going to do that today because we're gonna get root on this device a lot easier. And so we're actually going to run the command to tell the device to just go ahead and boot up. So we're just going to write backspace. Sometimes backspace doesn't work. So here we're going to boot up the device, and then we're going to watch very quickly. Now, let's that all happened really fast, so I'll scroll up and tell you what I did there. And obviously, I wouldn't know to do this the first time, right? I've been on this UART before. So here we can see it comes up and it says press the F key to hit enter to enter failsafe mode. So if you watched the last video that I made on our open source Linux router, our OpenWrt, and the hardware that's related to it, the OpenWRT1, on that system, we noted that on a production device that you were really trying to harden down, you know, especially if the device was claiming to, you know, stop all the hacks and malware, right? You wouldn't leave this compiled in. You would take the OpenWRT project and you would not compile in this failsafe mode, because what we can do with this failsafe mode, as you can see, is it just drops us into a shell, a root shell. Now, this is not the fully booted system as it would normally if we hadn't, interrupted it by hitting F and entering failsafe mode. It's not like that. So it's this special mode that allows you to recover a device, because with OpenWrt, you are oftentimes like hacking on a router that usually has proprietary software on it, and you're trying to like get this software to work, and you can do a lot of things to get it into a state where it's soft bricked, right? Where you don't have any kind of internet or networked connectivity to get a shell on the device to fix it. And so oftentimes you need to plug into the console and use failsafe mode to get yourself access to the device again, to fix whatever mistake you made in configuring it. But on a production device, again, that's supposed to be this like ironclad IoT defender device, you would not do this, right? You would compile this out. You would remove this failsafe mode feature. So we're going to show what we can do to get persistent access on this device now. So and it even tells us, it literally tells us what we can do. So it says all you got to do is you just got to run. Now we could run this, but we don't want to reset things to factory settings. We don't want to do that. We don't want it to potentially wipe anything. So we're just going to run this mount root command, and what that does is it mounts our root file system. It mounts this this overlay file system, which what this overlay file system is doing. Let's explain that by looking first at this file system right here. So we can see that this squashfs file system is mounted, it's like devroot is mounted on /rom, and it is read only, right? And so a lot of times on an IoT device, you'll find that the main root file system is read only. You can't modify it, and that's to give it some stability. So again, with these embedded devices, you can do lots of stuff. It can experience unexpected things that happen to it that will brick the device. And so one of the ways you can shield yourself from a lot of that is by making the root file system read-only. But obviously on a device, to configure it, you need to write to it. And so that usually happens in a different type of file system. A squashfs file system cannot be written to while it's on a running system, but a JFFS2 file system can, and so that's where all of these like custom settings are going to live, right? So we're going to then do, and it even tells us here, right? You run mount root, and then you run the password command, because if you ran the password command before, it would like error out. So now we can run the password command. And it says, changing password. Okay, it says the password is unchanged. Okay, there is our Etsy shadow. Okay, I'm trying to remember what the heck is going on with this device. Oh, I think I know what's going to happen. Yeah. I'm trying to remember now. Okay, so can I actually, because that file might not be editable. Can't read your input. All right. Let's see. Really? It's not letting me scroll up. Okay, that's fine. Okay, so yeah, shadow. I don't know why they renamed the root user to this weird, like to the same thing as the host name. Doesn't make any sense. Oh gosh, it's gonna reboot on me. I forgot. This thing is like a watchdog timer, and so it automatically reboots. It's probably gonna do that now, isn't it? All right. You know what? We're gonna let this device boot up without. Oh yeah. I remember now. Okay, so that's one way that sometimes you can modify a device and you can get into that root shell, right, with the failsafe mode. But we're gonna allow this device to just boot up normally, and then we're gonna see if we can see what's going on. Because I think I remember now what's gonna happen. No. Okay, let's get back into failsafe mode. All right, we're gonna restart. There There we go. Oh, no. We do it from here. There we go. Okay, failsafe mode. We got it. Yes, this is interesting because it's running. Oh yeah, it runs telnet. But I think that's a part of failsafe mode. Because here is their, okay, so this is where there's a bunch of their specific stuff. But I don't think this really matters right now. Okay. Let's go back to mount root. Okay. Our overlay. Okay. So what we want to do is in the overlay. Yeah, there it is. Like this is what I should be editing right here. So hang on. I'm actually curious what this is. Oh, those are like, okay. Let me just check. Yeah, there's nothing in there. I'm curious. Config. Oh, come on. I can't scroll up anymore for some reason. So, all right. Actually, I'm gonna like exit my. I'm gonna reset my terminal and reconnect. Okay, I fixed scrolling. There we go. All right. So here, obviously, we're like, this is the settings of OpenWRT, and so we can get some useful information out of here. Obviously, root password is on. I could drop there. Yeah. We don't really care about that right now. Okay, so we should be able to run. Oh, you know what? I wonder if the password command is all messed up because this is the user. All right, password password root unknown user. Yeah, you're right. Okay, you know what? So for some reason, the password command is like not letting us mess. Okay, can I go into this file? No. VI like refuses to work. Okay, so what we're gonna do is we're gonna generate a password with OpenSSL that we know. All right, so we're gonna go OpenSSL -1. No, it's like password -1, and then we're say password. There we go. There's a hash. And so now what we need to do is we need to echo, okay, so we want to do this, then this, and then the rest of this. Okay, so we're going to make this file. All right. I don't know how important these are, but we're just gonna put all of those there too. The network. Are you kidding me? We're good. And nobody. Okay. There we go. The file looks good. Copy A to shadow. Sync. There we go. All right. So we should be good to go now. And oh, yes. Another thing I want to do. D. Okay, so I want to look let's look in /etc. I'm gonna look in init tab. I forgot. I keep forgetting that Vim doesn't actually work. No. Okay, tab. Okay, here we go. We've got this stuff. So, oh, I need to put, because yeah, the UART interface ends up, oh, okay, it just rebooted. Dang it. All right, so we're gonna try to let it boot, but there's no, but there's no like actual interface. So that's why it dies here if you don't enter failsafe mode. Okay, that is good to know because we can try to change that. We can try to put init tab in the overlay and then add the console, connect that up to the TTY. But we're gonna move on to part 2 of our plan. So obviously we're able to like do some things in this like limited root shell, but hopefully we'll be able to do way more when we dump the firmware, and then maybe we can do a firmware modification that way in the future. So we're gonna go over to our desk and perform the firmware extraction now. So I'm gonna power off the device because we are going to do a full-on chip off firmware extraction. So to do that, what we're gonna do is we're going to use hot air on this flash chip right here. And I don't even think we're gonna need a microscope for this today. So let's just go ahead. Don't even need flux today. So we're going to pipe some hot air at this. Wait for the solder to liquefy. And hopefully we can do it without melting this thing next door. Come on. Do we melt some plastic? I smell melted plastic. That's good for your lungs, right? All right. So we got our chip there. And we have a number of these adapters, and I did not know exactly. I thought it was going to be the really small one, but yeah, okay. I haven't had one of these really tiny ones in a long time. Usually the form factor of these chips are, you know, one of these ones. So let's take a look at that under the microscope because I want to make sure that everything is lined up for our adapter. And the other thing we need to do is, oh, this is the right direction. Okay, because this is going to be, we're going to put this at the bottom of our adapter, but then pin 1, indicated by the circle, needs to be pointing up, which it looks good. We're doing that. Okay. Sweet. No, we can inspect that. No bridge solder. Let's focus that a little bit so you guys can see. Yeah, there we go. That looks great. Now, back over here. And so now we are going to use our brand new XGECU T76. So we've got the old one over here on the desk. The older, you know, bigger brother here. This is the T56. This is still going to be able to do pretty much everything that this can do currently, but I've just been kicking the tires on this device. It doesn't work. There's some things that don't work yet in it, especially in wine. So, but I have been working on that, and I have got it functional due to yeah, getting a fix for the wine USB driver. So, helping with that fix. It was mostly Radio Man V. Shout out to him. So, all right, so we're gonna drop it in like that. Again, I can show you in the software in a minute, but we are setting this all the way down towards the bottom. So we see here, there's a little like dot here that shows you that pin 1 is up in this direction. And so we wanna set it all the way down, but with pin 1 facing up in our adapter. And then we're plugged in over there to our USB hub, and then we are going to power the device on. And Now let's go over here to our desk. And we, yeah, so see here, when you select the chip, which I've already punched in this chip's model number right here. So once you do that, you come here and you say, hey, look, there's this little fancy diagram, which is usually correct. Sometimes it's absolutely wrong, and you just need to use your brain to be like, hey, that doesn't make sense. But here we can see that we're placing the chip all the way down at the bottom, pin 1 facing up. So we have that good to go. All these settings look fine. So now we are going to cross our fingers and we're going to do a read and hope that nothing is messed up or bridged or the pins aren't. Aha! Okay, the check ID failed. That is exactly, okay. Is the driver doing anything weird? See, this is exactly the type of failure that I was expecting out of this thing. And usually, if I just bump it a couple times, it will read. Check ID error. It's not even telling me what the check ID is. Okay. I'm gonna YOLO this and just tell it not to do that. Why not? What could go wrong? Well, it looks like we read it though. I don't know why it expected a different value for the check ID. Because what that is it's an initial interrogation of the chip to get some unique identifier off the chip that's unique per model. And there we go. There we go. Wine. You're crashing. This is why. This is a new. This doesn't happen with the T56, the old reader. There's something weird going on with the wine driver. But oh no, I didn't save the firmware. Gosh. All right, we're gonna do our read. No. Okay, turn check ID off. Read, and then I'm gonna get over here. I've got my save location. Okay, cool. We got it. File, save it here. Yes, we got it. All right, let's go away from there. So we are gonna figure out why, and then the wine driver crashes. We're working on that. We're working on getting that fixed. So we have our firmware file. That's awesome. Okay, let's run binwalk. Let's run binwalk in not big font. All right, there we go. So here we go. We have a U image firmware image here. This is at a really early decimal offset. So this is obviously a U-boot image. That's that bootloader code. We're usually going to see that at the beginning, at the top of the address space on a flash chip. Very common. Looks like we have another U-image firmware image here. Oh, our kernel. Okay, cool. Awesome. We have the Linux kernel image. Very cool. We even have identified the Linux kernel version, which is Linux 3.18.23, which is kind of old, just a little bit. Creation time, 2018. Again, we saw that before. And we see those file systems that we are expecting. We see a squashfs file system and a jffs2 file system. That is really cool. So now let's run binwalk with the -e flag thrown in there. And it's going to use the extractors. The extractors are not built into binwalk. They're external utilities. So for squashfs, I believe it's going to use unsquashfs or some other project. And jffs2 is going to use the Jefferson tool to perform the unpacking of those two file systems. So now, this is using binwalk v3, written in Rust. We're going to open, we can increase the font now because we're not trying to read that output there. We have firmware.bin, and so, okay, so we have a number of things that we've unpacked here, and we can actually list these files, which is cool. So let's go here and let's say less on these files. So we can see a whole bunch of files here. that we have. And so this high IoT, obviously that's related to the product here. That's not a part of the base OpenWRT image, which is of interest to us. So this is all this stuff is really interesting. But I don't think there's any like real binaries there, which is fascinating. So I'm just going to jump ahead in my train of thought. So when I watched this device over the network in Wireshark, what I saw was a request that would go out, and it was a DNS request that would fail, right? They took all their infrastructure down. But there was a DNS request that would go out to a certain server, and okay, so we have upgrade. That's probably not it. But there's going to be some code that it's almost like it's going out and trying to like download more code to execute, right? So that is pretty interesting. Bypass. What? What even is this? Okay, so we got a bunch of CA certs. Yeah. This is just like the trust store. Let's go down. No, not too far. Oh, I hit home. I went all the way back. Okay. But I think I have a plan to look for what I want to look for. And that's because I remember in the domain name, it said like Windows in the domain name, which is funny. Oh, here it is. Cool. So I grep for that. And here in daemon boot. Okay, daemon boot. It's echoing, source, cheesy, blah, 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 blah. Okay, so here we go. HTTP, high IoT, blob, core, Windows, net, packages, Akita. So obviously this is where it was going to go and like download the software onto this very bare bones OpenWRT image, and then it was going to apparently do all this stuff that was going to block hacks, right? Well, if it was going to do that, if this is a security device, why is it doing it over clear text HTTP and not HTTPS? Because this is a piece of snake oil software. That's why I'm answering my own questions. So, okay, so this is in this file, dist feeds. Okay, that's interesting. Oh, no. It's like writing that into the file, dist feeds. Okay, daemon boot. Oh, very cool. This is a script. No. You have to put the full path. Come on. Here we go. Okay, cool. So this is the unique special sauce that this company loaded onto this image here. So we have opt, high IoT, temp, device booted. Okay, some boot information. Very cool. So yeah, we're echoing into this O package dist feeds. Okay, so they're basically making their server host like a custom open package, right? Where it's going to download their software onto this device, which is a bummer because the servers are not up, so I can't get a copy of the actual software that's like claiming to like block all this malware. It's obviously snake oil. Yeah, so this shell script is super interesting though. While true, open package update, open package install daemon. Yeah. Cool. Yeah, that's fascinating. But we have the we have the stuff now, and what we can do with this is we can also do some firmware modification. So one thing that I would be interested in modifying and then either re-flashing onto the device, if we can't modify it on that overlay file system, again, like I mentioned, is the init tab file. And that's because in this file, we would see an entry. So this is where you can put an entry to say, to associate the console, like bin login, or you can put just bin sh. You can just have it drop you to a shell with a certain TTY interface, and we can figure out which one is the right one to set. So with a little bit more research, we can probably get a full persistent shell on the device. And so we're going to put this flash chip back on. We're going to wrap this up. So let's go back over here and let's turn that off. Grab our chip. All right, because we want to have a functional device again. Let's actually do this under microscope, just because. Okay, let's see what we got here. Yeah, you can see we burnt a little bit of plastic there. So what I'm gonna do is I'm gonna tape that off to try to shield this from heat. There we go. When we put this chip back on. All right. So what we're gonna do is now I am going to we'll clean this up in the proper way. All right. So we're going to throw down just a tiny amount of flux. Get out of here. There we go. And now we're going to get this heated up here, and I'm going to clean that old solder off there. I'm going to get some fresh, good solder. There we go. Looks good. Now we're just going to kind of put it in kind of the right spot. We've got a little bit of flux down, so hopefully we can just throw some heat down and it will flow to the right spot. If not, I'll have to coax it into the right spot with some tweezers. All right, I gotta switch hands. There we go. Ah. No, tape. My tape is pushing it away. That's hilarious. What the frick? Ah. All right, I realize that's like slightly off camera, but it's not out of my microscope. All right, we're just gonna remove that. We try to melt as little plastic as we can here. All right. Smells good. All right. So, as that cools down, we're going to slowly put these back on. There we go. All right, and we're just gonna validate that we didn't completely wreck everything. And we're gonna go back to our right. And you go back here, plug that in. And we are going to plug in our device and just make sure we get UART. Awesome. Okay, so we are back. Oh, wait. Yeah, no, that proves that the flash is good because U-boot is on the flash. So, so there we go. We have shown that we can get UART on the board. Obviously, we want to do a little bit more with that UART. And now what we're going to be able to do is reverse engineer some of the scripts that we got off of the device because of the flash dump. Next, what I want to do is there is a mobile app, and I can probably get a copy of the old Android app that's archived somewhere. And I want to do a deep dive on that to understand how it was allegedly scanning for malware, because I think it was actually coming a lot more from the mobile app than the IoT device itself, but that will remain to be seen. Thank you for watching this video. If you watched to the end, please subscribe if you're not subscribed. Let me know in a comment what you liked about this video, what you didn't like, and have a good day.